Welcome to the Businesstalk podcast. I am your host Deepak from India. Today we have the privilege and honor of welcoming Dr. Douglas Comer as our distinguished guest on the podcast. Before we begin, let me introduce our guest for today's episode. Professor Douglas Comer is a distinguished professor of computer science at Purdue University, renowned for his pioneering contributions to computer networking and internet technology. A foundational figure in the history of the internet, Professor Comer brings decades of pioneering experience to the intersection of computer science research, industry leadership, and education. As a former vice president of research at Cisco Systems and original member of the Internet Architecture Board, he played a hands-on role in shaping the early internet, making him one of the world's foremost authorities on TCP/IP protocols and internet technologies. Dr. Comer influence extend far beyond the lab and boardroom. His acclaimed three-volume internetworking series stands as a definitive reference on internet protocols, and his broader collection of best-selling books spanning computer networks, operating systems, and computer architecture has been translated into 16 languages and adopted by universities and industry professionals across the globe. A gifted communicator as much as a scholar, Professor Comer has lectured to thousands of engineers and students worldwide and served for 2 decades as the editor-in-chief of the journal Software Practice Experience. A fellow of the ACM and the recipient of numerous teaching honors, his career reflects a rare and lasting commitment to advancing both the science and accessibility of computing. Dr. Douglas Comer is a recipient of the prestigious Internet Hall of Fame Award, one of the highest honors in the field of networking and internet technology. In today's episode, we sit down with Professor Douglas Comer to explore the fascinating insights from his acclaimed book, the Cloud Computing Book, The Future of Computing Explained. It's my pleasure to have him with us. Please join me in welcoming Professor Douglas Comer to the podcast. Professor Douglas, thank you for joining us. It's a true honor to have you on Business Talk today.
Oh, thank you for inviting me.
Professor, cloud computing has evolved rapidly over the past decades. In your view, what is the single most transformative shift that defines where cloud computing stands today and where it is headed next?
Well, it's still a young discipline. If you go back to, say, 2005, no one believed that cloud computing would be what it is now. And it's taken off. There are new technologies, new uses, new ways to use cloud. One of the things that's really interesting is that AI requires lots of parallel computing, and cloud is ready. That's what cloud does. So all the AI folks are using cloud, and we don't know what's going to happen next. But there are certainly data centers going up all over the world like crazy. So we can predict that it will certainly blossom in the next 10 years.
Professor, your book emphasizes concepts and principles over specific vendor products. In a world dominated by AWS, Azure, and Google Cloud, why is that vendor agnostic approach so critical for the next generation of engineers and IT leaders?
Well, it works this way. I told you it's a young discipline and everything keeps changing. Even AWS has come up with new products they sell, new services, new technologies. Azure, same thing. There right now it's hot to do new security things, and I think it's important. I tell students all the technologies will change. When I was writing the book, I started to interview CIOs, engineers, all who are using, building cloud, whatever. And I made a list of all the technologies to be included. By the time I was finished, half of the things on my list were gone. And so I tell students the most important thing you can learn, if you're starting out to learn about cloud, get the concepts, understand the concepts. That way, when a vendor comes along and says, I have this brand new thing that you've never heard of before, you can spot it right away and say, oh, That's just a re-implementation of MapReduce, or that's just the vendor's version of microservice. So that's my pitch to students. Learn the concepts, they will last, but the technologies will not last.
Professor, virtual machines and containers like Docker are both central to modern cloud infrastructure. How would you explain the key difference between the two to someone just stepping into the cloud world? And when should organizations choose one over the other?
Okay, so it's actually pretty straightforward. If you're just stepping into the cloud world, what you want to do is, now I'm not talking about individuals, I'm talking about enterprises and other big organizations, move their computing to the cloud. They are going to be leasing facilities in the cloud rather than having facilities on premises. And virtual machines were the first, well, not the first, actually. In the early days of cloud, people were actually leasing physical servers. They would go to a cloud provider, and the cloud provider would say, I can lease you a whole rack of computers, they're called servers, and it costs this much per month. That didn't last long because you can see that physical allocation is not a good paradigm. But a wonderful technology came along, virtual machines. Virtual machine, if I explained it to you before you knew it was possible, even engineers thought it was just a miracle. Here's the deal. I can take a very powerful computer. So don't think, a PC or a laptop. Think a processor with hundreds of cores, with more gigabytes of memory than you can imagine. So very powerful computer. I can use virtual machines in the following way. I put a funny piece of software on there called a hypervisor, and the hypervisor can create virtual machines. When it creates a virtual machine, that machine looks like, acts like a real computer, but you can have multiple of them running on the same physical computer. Isn't that great? So the cloud providers started out saying, we're going to lease facilities, and then along came virtual machines. This was great. They didn't have to lease a physical server to a particular client. They could lease a virtual machine. And if the customer said, hey, next month I need more virtual machines, not a problem. They're created by software. So create them, keep them for a month. So, most businesses have peak times, and they only need a whole bunch of computers during the peak time. And they can, with the cloud stuff, with the virtual machines, the cloud provider says, you can lease whatever you want, and we'll only charge you for what you use. So that lasted maybe 10 years, and everybody seemed very happy. Basically, they had moved all of their normal computing to the cloud. And if they had a computer at their enterprise before they went to cloud, they would lease a virtual machine. They would put the same operating system, the same applications. They just basically moved that computer to the cloud. And they would do that for all the computers in their shop. But that's not the best way to use cloud. The best way to use cloud is to use it for scalable computing. So yeah, everybody had their old-fashioned distributed computing systems at their enterprise, and they could use virtual machines to do exactly the same thing. But what about scalability? Let's take, you want to set up a website, so somebody's using the cloud, some enterprise X is using the cloud, and they want to allow their customers, to come along and get to their web page to order things. How many virtual machines should you lease? Well, now you have to ask, I don't want to lease too many because I have to pay for them. If they're sitting idle, I'm paying for them. On the other hand, if I lease too few, my customers will try and get in, and they will find that they can't get enough, they can't get a response. along came a new technology, the container technology. Container technology, don't think of replacing a complete computer. Think of replacing a running program. If you're an engineer, you call it a process. So when we have a normal computer and a customer comes along and makes a connection for a web page, they get a process to handle their web page. In the container world, they get a container. So every time a customer comes along, and containers, by the way, are very lightweight. It doesn't take much computing power or time or space to launch a container. It's much more like launching a program. So it's compared to a virtual machine runs a real operating system. So it runs one operating system on the virtual machine, and then it has applications on top of that. If you want another virtual machine, you start again and you launch an operating system, boot the operating system, and then boot applications. With containers, you don't do that. You just launch a container. So every time you need to answer a request coming in, launch a container. Very lightweight, very efficient, and by the way, since this is for the business world, very cost effective. It costs a lot less. So that basically modified the way people were thinking. Now we can scale things in order to handle customers or whatever need we have, whether it's customers coming in or suppliers contacting us or any kind of services that the business does, whatever my business is, I can scale to handle it and only pay for what I use, and the scaling can be really fast. So by the time we get to, 2022, somewhere around there, containers had taken over. So for 10 years, it was all virtual machines. And then the next 10 years, just moved to containers. By the way, there's a name for what we're doing. The cloud world calls it cloud native software. That is to say, instead of taking the old software and just running it in the cloud, build software in a new way that can run in the cloud. And containers are the basis for much of the new way.
Professor, why did data center network architecture evolve from the traditional fat tree model to the modern leaf-spine design? And how has this shift redefined scalability and performance?
All right, so in the early days, all of the large data centers weren't really cloud computing data centers. They were large websites. All the search engines and the Facebooks of the world, the social media people, they each had a very large website. If you think about a website, all the requests come in from the internet and then are handed to one of the computers inside, and the responses go back over the internet. So the network architecture was set up to do that. There was a very large, high-speed connection between the internet and the data center. And then the traffic was split off among racks and among servers in the data center. The technology used to split it off is called a load balancer. We still have load balancers, but they're no longer hardware devices. They are all done in software. Anyway, in that world, the connection to the internet at the top of the data center to get from the data center out had to be really, really fast because all of the traffic was going over that connection. And then the connections further down toward the racks could be slower because we're dividing it. If we have a load balancer dividing it among 1,000 racks, each rack only gets 1/1,000th of all the traffic. So all the vendors building network equipment came up with this paradigm where it was a fat tree. They sold a very high-speed network for the very, very top connection to get to the internet. Then they sold slower, and by the way, much cheaper equipment to use to get inside the data centers and down to racks, and then slower but much cheaper equipment to get from the top of a rack switch to individual servers in the rack. That lasted as long as people had all the traffic coming from and going to the internet. Now we get to cloud computing. An enterprise is going to move all its computing into the cloud. And what happens is, if you think about what happens on a campus from an enterprise, they've got lots of computers all over. Maybe the HR department has the HR database. Maybe the accounting people have the accounts database on a server. And now when you do something inside the organization, you send traffic to one of the servers in the organization. When we moved to the cloud, that's what people found. Suddenly, traffic wasn't going just from the internet in and from the inside out to the internet. It was going across the data center. Multiple servers that are owned by a given organization, they're sending data back and forth. That doesn't work well with the fat tree, because in the fat tree, and by the way, tree is a technical term. It's a description of how the network is organized. There are no loops. In a fat tree, it had all the data has to go from a server up through the rack, up to farther up the tree, and then back down to another rack and down to another server. So the center of the tree was getting a lot of traffic. Vendors couldn't keep up, building higher and higher speed networking equipment to handle the highest speed parts of the tree. Along came an idea, which is really funny because it's an ancient idea. It's been around forever. It was pioneered in the telephone system by a guy named Clos. If you're French, you say Clos. A lot of people say Clos. Anyway, he had this idea about how to build a network that could support lots of traffic. And technically, what the data center people adopted, it's called leaf spine, is technically a folded claw architecture. And what it means is, first of all the connections in the internet, inside the data center, are the same speed. You don't have to have very high speed connections and very slow speed connections. You can use standard speed connections everywhere. Furthermore, this architecture offers the ability to do two things. One, redundancy, and two, parallelism. So the beauty of it is, if you have a spine with n spine switches, then there are n paths to get from every server to any other server. If one of them fails, the hardware automatically reroutes things so that we're not talking routing software. It happens instantly. The hardware just shuts down that path and redoes things so that you use the other paths and you use them all in parallel. The technology is called equal cost multipath forwarding, and it's a beautiful hardware solution. So why did leaf spine take over? Because in the cloud world, we have lots of traffic going from one server inside the data center to another one inside. It's called east-west traffic. And if you draw the pictures right, then you draw the old tree with the internet at the top and all of the servers at the bottom, and then the traffic is north-south. And if you draw two servers in the data center, they're talking to one another. You draw them in such a way that it's east-west. Get it? So the east-west comes from just the figure that you draw. Anyway, we now have leaf spine working extremely well. It has many advantages. It is incrementally upgradable. You just can add more racks. You can add more spine switches. You can add another, if you get really, really big data centers, you can add another layer of super spine switches. Just replicate the same idea one layer up.
Professor, storage in the cloud, whether SAN, NAS, or object storage, can be a maze for IT managers. What mental model do you recommend for organizations trying to choose the right storage strategy as they migrate to the cloud?
So let's start with the terminology. SAN stands for Storage Access Network. And in the early days, in order to get from a computer in the data center to a disk storage, you had to have a special network. That's all gone, but the terminology persists. So we're using leaf spine network everywhere, including for storage access, but the vendors still call it a SAN. So what are they selling? What are they selling? What they're really selling is this. If you have a virtual machine, you need to have, just like a real machine, you need to have a network connection and you need to have a disk, at least one, maybe more than one, but you need to have a disk. And that's what SAN provides. So a SAN storage server in a data center provides the illusion of giving a disk to each virtual machine. I say illusion because it's all done in software, it's virtual. You don't actually allocate a physical disk. So the SAN storage server has a bunch of physical disks, but it really allocates blocks on those disks to individual servers in the data center, and the server looks like it's accessing its own disk. So we get virtual disks. So SAN is disk. Why don't they just call it a disk storage system? It bugs me. Then along came remote file systems. And we've been using remote file systems. In fact, most enterprise use NFS to have remote file system access somewhere in their enterprise before they ever moved to cloud. And so along came the cloud, and people said, let's put NFS remote file systems in a cloud. Well, they couldn't settle for just putting a remote file server there. They couldn't call it a remote file server. No, they had to call it something cutesy. So they made up the term network attached storage. Why did they choose that? Because they had SAN, and now they get network attached storage. The acronym is SAN backward. This is nerd humor. Unfortunately, it still persists, and that little bit of nerd humor makes it completely confusing. So SAN, remote disks. NAS, remote files. In fact, if you think about it, if you've ever used NFS for your remote files, think about the ends. You see NAS. In fact, most NAS systems, many NAS systems use NFS as the protocol. So think NFS files on a NAS system. Okay, one more step. That works great if you're using virtual machines, or even if you're using containers. Containers usually use virtual files, so they go to the NAS system. So think of virtual machine, SAN, disks, containers, files, NAS. Anyway, that all works great until we get to data centers that are processing things that are huge. How are you going to put 4 petabytes of data in a file? Well, guess what? File systems are meant for smaller things. Now we think, oh, if you're going to have terabytes in a file, yeah, you can, but that's the extreme of a file. And for people that have petabytes or people that have zettabytes, it gets out of hand. Furthermore, lots of things in the data center need redundancy. They need redundancy for two reasons. One is for protection in case something goes wrong, but they also need redundancy because they want to have multiple programs accessing the same objects at the same time. That's where we get to object storage systems. So these are unlike anything that you've seen in the past. We always had disks, we always had files. Object store is completely new to cloud. What can you do with an object store? You can store very large objects. You can access them from multiple places in the data center at the same time, but you can't do partial reads and writes. You can read an object, you can append to the end of the object, you can write to an object, but you can't go to the middle of it and change a few bytes. Now, you can do that in a file, but you can't do that with an object. So, many applications in a data center prefer objects because what they really do is they process huge amounts of data, and they do so sequentially, and they do so in parallel. So object store works well in those situations.
Professor, Kubernetes has become almost synonymous with container orchestration. What conceptual problem does orchestration solve that automation alone cannot? And why does that distinct matter at enterprise scale?
Well, data centers have always been about automation because when you get to the scale of a data center, manual processes just do not work. Even things like allocating a VM. If a customer had to call up a human and the human had to type, I want to allocate a VM, please find a server and please allocate, that's incredibly slow. So we've always had a lot of automation in the data center. When containers came along, we had a wonderful technology that could do exactly what you want with scaling. So I'll take that as the first thing that really motivates orchestration. Whenever a connection comes in, I would like to launch a new container. So, because I'm now an enterprise in the cloud, and I've got customers that want to go to my website to buy things, whatever. Every time a customer contact comes in, I want to launch a container. Again, couldn't possibly do that manually. How would we automate it? Well, launching a container has several aspects. One, you have to find a place to launch it. So you have to find a lightly loaded, and that's an important part, a lightly loaded server where you're going to run it. You have to hook up the network so that the person outside can contact that container. So we have to do network routing inside the data center. Second, we have to do storage. That container, when it runs, is going to have access to files, typically files, maybe objects, but you have to make sure all of that's in place. So now we've got a bunch of things to do. Enter orchestration. The orchestration systems do all of that to manage scaling containers and container-based services. In particular, we no longer think of just a container. With orchestration systems, we think of a service. So you give a service a name. It is my web service. So I give it a name. It's actually a domain name. Think of a URL. And now that service is known only by that name. Internally, there are a bunch of containers running, and there's a bunch of network routing that has to be done so that when a customer comes in, they always go to the same container. But that's all handled by the orchestration system. So all you do, Kubernetes is the standard orchestration system that everyone uses. All you have to do to use Kubernetes is write a specification file, template, sometimes called a manifest. There's bunches of names. In fact, one of the worst parts of cloud is there are multiple names for the same thing. And depending on who you talk to, you might want to use the right, the name they prefer. Some prefer manifest, some prefer configuration file. In any case, you write this template, manifest, configuration file, you write it down. It's fairly straightforward. Think XML style of writing things. And it specifies what is to be done for this service. Kubernetes takes over and it will handle all of the details. Once it's running, somebody contacts the service, it automatically launches the container, figures out where to run it, figures out how the network ought to be changed so that the incoming request can go to it, may involve creating a proxy, and figures out how to make sure that the container can access the NAS system that it needs for files. So if you haven't done it, it doesn't sound like much, but there's a zillion details here that I've just glossed over. By the way, you can't set up routing in the data center. You have to go to the cloud provider's software and make a request to do that. So Kubernetes isn't just doing things. It has to interface with the cloud provider to do some of the steps.
Professor, microservices and serverless computing represent two very different philosophies of cloud native design. How do you guide software engineers in deciding which approach best fits their application architecture?
Like any engineering task, there are a bunch of variables that you have to consider. All the things in terms of size of the problem, type of the problem, computing to be done, the weight of how much things like network communication versus computation to do. So I'll give you, so that's the setup that it's actually a hard thing to decide. You can't, there's no simple solution, but I'll give you a primer on how to do it, okay? Just the basics. Here's the idea. If you have an application, a giant old-fashioned application running before you got to the cloud, and you now want to run it in the cloud, and you want it to do cloud native scaling, one of the things that you should consider is microservices. Because microservice approach says, take that big old application, identify modules in it, and make each module a container. And then set it up so that when it runs, it automatically invokes containers as needed. Now, in the old-fashioned world, that big giant application had all the code in memory at the same time. All the modules were there. When it wanted to invoke one of them, it just did a jump subroutine, call to a subroutine, or a function invocation, a method invocation, depending on, again, your terminology. But it was all internal, simple machine instruction to do that. In the cloud world, we're going to be running each container in a separate, possibly a separate computer. And so when one of them wants to invoke another one, it has to go over the network. Right? Microservices says you get a really big advantage by doing it that way. Now, it sounds like you're actually making a lot of work, but the big advantage is scale. You can scale an application because it's not running on one machine anymore. You don't just get an old virtual machine and run the same application you ran. Divide it into containers. One container per module, call each of them a microservice, and then you can scale that as needed. If you're a software engineer, imagine a computer program running. It's got a big computer program. Imagine you're running, I don't know, Microsoft Word. Microsoft Word has a zillion things in it that most users never ever use when they run it. if we scaled it by replicating Microsoft Word, that's a huge thing to replicate. But if we break out every little piece of Microsoft Word, every little module inside it, and we only replicate those modules when needed, then the standard user could start out with a couple of modules. Just I'm typing and and now I want to insert a table. And maybe at that point, it requires you to get a new module. So we spawn a module and a container for that module. But we don't have to replicate the entire gigantic thing. We only have to replicate the modules as needed. So that's the microservices version of how to do cloud native stuff. Great. There is another approach, and you mentioned it. It's the serverless computing approach. What is serverless computing? Well, first of all, most importantly, you should understand is it uses servers. It's not serverless at all. That's another terrible name. But it caught everyone's attention. It certainly caught my attention. The first time one of my colleagues said, "Have you heard about serverless computing?" I thought, no, I haven't heard about it. It's crazy. All right, so here's the deal. Serverless computing means you hire the cloud provider to handle part of running a server. In the old world of running servers, if you were a software engineer and you were writing server software, you had to write two pieces. One is what the business world calls business logic. That is to say, a program that handles the business's stuff. If you're a tax accounting firm, then it would be the software that handles tax accounting. If you're a jet ski seller, it would be the part that handles sales of jet skis. Second part. So that's the business logic part. The thing that you also have to write is the part to manage the server. In the old world, you had to invoke a new thread or a new process every time a connection arrived. In the cloud world, it's much more complex. In the cloud world, we're doing containers. So you have to launch a container to handle the new function. All right. So the cloud providers saw this as an opportunity for income. They said, look, you don't really want to train your software engineers on how to launch containers in my cloud. In fact, most enterprises don't use one cloud provider. They use multiple cloud providers for safety so that they don't get locked in. And the cloud provider said, look, you're using Azure and you're using AWS. You don't really want to have to train software engineers on how to do container allocation in Azure and container allocation in AWS. Why don't you just pay us to do all of that part for you? You, of course, still write the business logic. You're selling jet skis, you still write the jet ski sales program, whatever it is that it does. But we'll handle scaling it. We'll handle, launching all the containers. And by the way, you can tell us how much scale to use. One of the problems is there are bad guys out there. If I have a service, if I'm using the cloud and I have a service and I don't put any limits on, as people found out very early in the cloud days, anybody could come along and start trying to access their service, and they would be creating either virtual machines or containers or whatever they were creating. Let's just take containers these days, and they pay for them. So a competitor could drive them bankrupt. I'll just make a zillion requests and I'll just keep the line open and I'll send one character at a time. I won't, I'll be pretending I'm typing in a question. And these guys are going to have to pay for 1 million open connections and they'll lose money. So that actually happened. And so now, when you do serverless computing, in fact, when you use Kubernetes, when you do Kubernetes to do microservices, you set limits on what can be done, how many, well, what's the maximum I want to allocate, and what's the minimum. You want minimum because if you have zero, then the first customer to come along takes a long time to start up. It's got to get Kubernetes to launch the initial container, and right, it's got to all. So specify minimum, specify maximum, and they tell you how much they'll charge to manage this little server for you. Very nice. It works okay. It works best if you have very large things to handle. One more thing I mentioned the cost. I should also say that there is a way that even startups can use serverless computing. The vendors offer a way to scale down to zero. So there's scale down to minimum or scale down to zero. And the scale down to zero is intended for startup companies. They don't have any money to put up. So they don't want to waste, they don't want to say, hey, always keep 10 containers running for my service. It's a startup. How many people are going to actually try it? Probably no one for the next month, So they want to scale down to zero. So there is that option. Anyway, what really works well with the serverless approach is if you have very large things. Think of a physicist. They do an experiment on a super collider, and they get all this data. They get petabytes of data. And now they have to process it. And we, in academia, we joke that what they do is they take petabytes of data, they number crunch it, and they come up with one floating point number at the end. 52.765, that's the answer. But in any case, they're going to have to do this. So how do you do it with serverless computing? Well, the beauty is with serverless computing, you can say, I'm willing to divide this into, pick a number, 500 parallel computers to make it go fast. So I take my data, I'm going to divide it into 500 chunks, pass them off each chunk to a computer, to a separate container running on a different computer, and they all run in parallel. Then I get my answer 500 times faster. Right, so who else might use this? The canonical example is Netflix. Netflix is in the business of doing distribution of video. So a content provider will come up with a new movie. They upload it to Netflix. They have a contract with Netflix. They upload it to Netflix, and Netflix has to process the movie. They have to do, among other things, some transcoding on it. They may have to insert ads. They do processing. And to do that, they use serverless computing. In comes the new movie. They divide it into chunks of video, a few minutes per chunk, because they can do all this in parallel. And so they divide it up, and then they send it off to parallel processing, and they use serverless computing. Serverless computing has another feature, at least most of the implementations I've seen have it. They have an event-driven mechanism. You don't have to pre-plan things. You build a piece of software that takes your movie, divides it into 5-minute chunks, and puts each of them as an object in an object store. And you set a trigger that says, when a new object arrives in this object store, please trigger this serverless function. So, new object arrives, serverless function gets triggered automatically. See how easy it is to write the code to handle this now. You don't have to know anything about how to launch servers. It's completely automated. It works really well for big chunks like that because they work well with objects. You can use the triggering mechanism to stimulate the system to do serverless computing. It goes off, takes the chunk, hands it off to a container to process. When that container finishes, that container puts it in another object store, another object bucket. And once again, you use a trigger to trigger the fact that you have to put these things all back together, right? If I've used 500, if I divided up my movie into 500 pieces, all 500 are being processed in parallel, and they will eventually end up being put into the done bucket. And every time one comes in, now I can figure out which piece that is. Do I have all the pieces? Can I start putting this back together again to form the final movie? So microservices work well for dividing things up. Serverless computing works well if you have large chunks of things that you want to automate the entire process of doing the processing.
Professor, security in a cloud environment introduces challenges that on-premise infrastructure never had to face. What do you consider the most underestimated security risk organizations face when moving to the cloud?
Well, in the old world, we used perimeter security. We had everything inside an organization was locked down, and we had firewalls so that nobody could get into the network from the outside. And that was an easy way. Anybody inside could get to anywhere, but people on the outside couldn't get in. And when you get to the cloud, of course, we're going to have a cloud data center with multiple cloud customers. Cloud customers, by the way, are called tenants because they lease facilities. So we're going to have multiple tenants all running in the same infrastructure. They may have two virtual machines by two different tenants running on the same physical server. We may have containers by different tenants running on the same physical server. All of the tenants are using the same underlying physical network. So in the early days, people worried a lot about shared infrastructure. Maybe there would be a leak. Somehow somebody, one tenant could find out what another one was doing. Even if they couldn't change it, they could wiretap it. Maybe that would happen. That has pretty much been decided to be not the big problem. Of course, there will always be situations where somebody figures out how to, break security. But the cloud data center people are actually pretty good at doing cloud security. The hard parts. There are two hard parts. One hard part is the interface between the tenant, what they want to achieve, and the actual cloud facilities that do that. So a tenant, obviously, I want to have a completely private network. All of my virtual machines and containers should be on the same network, and it should be completely detached from everybody else. No one should be allowed to see what I'm sending. No one should be allowed to send to my network. No one should be allowed to, I want to be isolated. Good. What about firewalls? Well, I want some firewall rules. I want to allow anybody to access my external web server, and I will tell you which server that is, and I want to allow that access. I don't want you to access my HR server or any other, functions that I'm running inside. So, well, that seems like I've explained it pretty well, don't you think? But now here's the thing. The tenant has a whole bunch of virtual machines and containers running on their network. The cloud provider can provide a way to isolate the network, and it's called virtual networks. And it's a beautiful idea. And they can guarantee that connections between a virtual network and the external network or go through a firewall. Now, I have to specify, if I'm a tenant, I have to specify exactly what firewall rules I want. Unfortunately, every cloud provider has their own interface for specifying firewall rules, for specifying deep packet inspection, for specifying any security thing. That means that a tenant has to learn, if you have multiple cloud providers, you have to learn each of them and get it right. And I say, number one, I've had people tell me that number one is they didn't understand exactly what they were specifying on the vendor's webpage, on the cloud provider's webpage, when they tried to specify firewall rules or when they specified what they wanted. So there's a gap between what I think mentally and when I go to enter it. How do I enter it in a way that it matches exactly what I'm thinking? Because I'm dealing with a language provided by a cloud provider, right? It's not a real language, but it's a, commands and web page and clicking on this, and that's number one. I think there is a bigger threat, and we are just starting to see the beginning of it. I think the biggest threat is what the business world calls the supply chain vulnerability. And in this case, the supply chain vulnerability is for software, believe it or not. How do you build a container? Well, it's not like the old days where a software engineer sat down at a screen and started typing lines of code. Nope. Containers are wonderful because you don't have to write much code to do standard things. All the code has been previously written and is available in repositories. So if you're a software engineer building containers, say, well, let's see, I need this base image. That's one of the first things you have to put in a container. I'll just go to the repository and grab Alpine, and it's a very standard one. I'll put that in. Now I need a web server. I'll go to the repository and get the web server software, put that in. My container's all built, it's done, it runs. Everybody's happy. But the vulnerability is there's no real safeguards on repositories. Almost anybody, and the repository people say we try and limit who can access it, but almost anybody can contribute to a repository. It's open source. One of my colleagues said, repositories are the Wild West of cloud computing. There are no rules, no laws, and no sheriffs. So the vulnerability is this. Suppose you go out and you get some web server thing and you put it in your container and you're running it. You know where you got it, but you don't know who contributed it. And furthermore, you ready for this surprise? When somebody built that image that they put out there that you downloaded, they might have gone and gotten it from other places and put together pieces to get that image built. And there's no control over that. So how far back do we go? That's where the supply chain vulnerability comes in. Somebody inserts some malware in some piece of software that gets included in a container image and gets put in a repository that somebody uses to build another piece of software that gets put into a container, into a repository. So now we've got another container image. Hidden way down in the bottom of all this is the malware. And of course, it's disguised. So maybe it's a trapdoor, maybe it's whatever. But now you download that and put it in your software, you may be vulnerable. And we've seen situations where this happens. So I think that's going to be the big thing that happens in the cloud world. Almost everyone is using open source software. I heard a lecture from a guy from Microsoft that said 65% of the workloads running in Azure was once all Windows. 65% are running on open source software. So we're using it everywhere, and we don't know what vulnerabilities are in it. I'll give you one more example of something that somebody did. There was a bad guy who wanted to introduce some malware, and in order to do it, made up a name for a file in a repository that was almost identical to a well-known file name. And then he put a version number on it that was much higher than the version that the standard version was running. And somehow, I don't know whether it was a search or AI or something, found the new higher version number. And in the software engineering world, there's a rule that says you should always upgrade to the latest version because it has the software protection. All the security stuff has been fixed. It's been protected. So they had configured their system to automatically select the highest version of anything. They rebuilt containers, selected the highest version, got the fake version that had the malware in it. See how this works? I think it's a very dangerous proposition. We're running software that no one has vetted. We have no way of knowing what's inside.
Listeners, that brings us to the end of today's fascinating conversation with Professor Douglas Comer. It's rare to speak with someone who has not only witnessed the birth of the internet, but actively helped build it and is still shaping the mind of the next generation through his writing and teaching. Professor, your insights today have given us listeners a truly rare window into the past, present, and future of computing. We are deeply grateful for your time and wisdom. Thank you once again, Professor Douglas Comer.
Thank you. Of course, if anybody needs somebody to come out and talk to them about cloud or internet, I do that as well.
Thank you so much, Professor.